Today we introduce three important continuous time signal types, starting with the sinusoidal signal. The general form is f of t equals k times sine of 2 pi ft plus w0. Here k is the peak amplitude, the maximum value the signal reaches. The parameter f is the frequency in hertz, which tells us how many complete cycles occur per second. The period t equals 1 over f, giving the duration of one cycle. The phase angle w0 shifts the signal along the time axis. We commonly define the angular frequency omega as 2 pi f, measured in radians per second. This gives us the equivalent form. F of t equals k sine of omega t plus w0. Let's visualize a sinusoidal signal. Here we plot sine of omega t with amplitude k. The peak-to-peak height is 2k, and the distance between two consecutive peaks gives us the period t. When we add a positive phase w0, the entire waveform shifts to the left. A negative phase shifts it to the right. The shape of the wave remains unchanged. Only its position along the time axis changes. The angular frequency omega controls how rapidly the signal oscillates. Let's compare how each parameter affects the waveform. In the first panel, we vary the amplitude k while keeping frequency and phase constant. A larger k stretches the wave vertically. In the second panel, we change the frequency. Higher frequency means more cycles packed into the same time interval and a shorter period. In the third panel, we adjust the phase angle. The wave shifts horizontally, but its amplitude and frequency stay the same. These three parameters, amplitude, frequency, and phase, completely determine any sinusoidal signal. The second signal type is the exponential signal. The one-sided form is f of t equals k e to the negative at times u of t. Here k is the initial amplitude at t equals 0 and a is the decay rate. A larger value of a means faster decay. The unit step function u of t ensures the signal exists only for t greater than or equal to 0. Without the unit step, we get g of t equals k e to the negative at, which is defined for all time. It grows exponentially for negative t values. Let's compare these two exponential forms side by side. On the left, f of t equals k e to the negative at times u of t. The signal starts at k when t equals 0 and decays smoothly towards 0. For negative time, the signal is exactly 0 thanks to the unit step. On the right, g of t equals k e to the negative at without the unit step. For positive t, it looks identical, but for negative t, it grows without bound. In practice, the one-sided exponential with u of t is far more common in physical systems. Our third signal type combines both concepts, the exponentially faded sinusoidal. It's defined as f of t equals k e to the negative at times sine of omega t plus w0 times u of t. The sinusoidal part creates the oscillation, while the exponential term k e to the negative at acts as a decaying envelope. As time increases, each successive peak is smaller than the last. This signal appears naturally in many physical systems: an underdamped spring, an RLC circuit after a switch is closed, or any system that oscillates while losing energy. Today we covered three continuous time signal types. Sinusoidal signals are defined by amplitude k, frequency f or omega, and phase w0. The exponential signal ke to the negative atu of t models one-sided decay, while removing the unit step gives a two-sided exponential. The exponentially faded sinusoidal combines oscillation with decay, capturing the behavior of many real-world damped systems. In the next lesson, we'll review discrete time signals and explore even-odd decomposition.